Hello, welcome to another module in this massive open online course. Let us continue looking at examples, and in this module let us start looking at examples pertaining to duality. Okay, so we want to start looking at examples related to concepts of duality. Okay, and what we have seen is the following. Let us start with the first example, that is something interesting, pertains to this concept of a dual norm. Okay, and now the dual norm, for instance, if you have a vector x bar and this is the L norm, alright, for instance L can be 2, that is the L2 norm, or 1 L1 norm, and so on. Now the dual norm of this is denoted by norm Z L star, which is defined as the maximum of Z bar transpose U bar over all elements such that norm of U bar L is less than or equal to norm of U bar L is less than or equal to 1. Okay. So this is basically the dual norm. So this is the L, this is the original norm, and this is basically the dual norm. This is the dual norm. Okay, and now for instance let us look at some examples. Of course this is simply a definition. Let us look at some examples to understand this. Let us consider L2, that is we are talking about the L2 norm. We are talking about the L2 norm. Therefore what is the dual norm? That is the dual norm of the L2 norm is maximum over all Z bar transpose U bar such that the L2 norm of U bar is less than or equal to 1. For instance, now let us look at this. Let us look at, so this is basically, now if you look at this, you have this maximum of Z bar transpose U bar over all such vectors norm U bar 2 is less than or equal to 1. This is the pertinent optimization problem, and of course you can see this is convex in nature because this is a linear objective convex constraint. Okay, and now this is easy to solve. In fact, we know that magnitude of Z bar transpose U bar is less than or equal to, in fact Z bar transpose U bar itself is less than or equal to norm of Z bar into norm of U bar. So we know for two vectors Z bar and U bar, Z bar transpose U bar is less than or equal to norm of Z bar times norm of U bar. Alright, the dot product is less than or equal to the product of the norms. This follows from the Cauchy-Schwarz inequality. This is from the now we know that this norm U bar is less than or equal to 1, which basically implies Z bar transpose U bar is less than or equal to norm Z bar times norm U bar, which is in turn less than or equal to norm Z bar, because norm U bar is less than or equal to 1, which implies that basically Z bar transpose U bar less than or equal to norm Z bar. And when does the maximum occur? We know the maximum occurs when U bar is aligned in the direction, when maximum for U bar is aligned with Z bar, u bar is aligned with z bar and norm u bar equals 1, which implies u bar equals z bar divided by norm z bar. So, the maximum occurs when u bar is z bar divided by norm z bar, and the maximum is z bar, the maximum equals, well, z bar transpose, substitute instead of u bar, substitute z bar divided by norm z bar. So, this is norm z bar square by norm z bar, which is norm z bar. Of course, all these are two norms, because as I mentioned, when there is no norm mentioned, by default equal to 2 norm. Okay. And therefore, you observe something interesting. What you observe is that the dual norm of the 2 norm equals the 2 norm itself. Okay. So, this is very interesting. Dual norm of the L2 norm is the dual norm of the L2 norm is the L2 norm itself. Okay. Now, let us look at another interesting dual, consider on the L infinity norm. We want to ask the question, what is the dual norm of the L infinity norm? Now, remember, L infinity norm, that is norm of L, norm of u by the L infinity, is simply the maximum of magnitude u1, magnitude u2, magnitude un, or simply the maximum of the magnitudes of all components of this. Now, what is the dual norm of the infinity norm? That is norm z bar of infinity, dual norm, is the maximum, that is your maximum of z bar transpose u bar, such that the infinity norm of u bar is less than or equal to 1. Now, what is z bar transpose u bar? Now, norm infinity norm of u bar less than or equal to 1, this implies maximum value of magnitude ui is less than or equal to 1. Now, assume z bar and u bar both to be n dimensional vectors. Now, what is this? This is simply equal to summation I equal to 1 to n zi times ui. Okay. And now, if you look at this, now therefore, now this is your z bar transpose u bar, which is simply the dot product between two. So, summation of component y, that is summation of component wise product, that is summation of I equal to 1 to n zi times ui, where n is the dimension of each vector. Now, this is less than or equal to, obviously, summation I equal to 1 to n magnitude zi magnitude zi times ui, which is equal to summation I equal to 1 to n magnitude zi magnitude ui. Now, we know magnitude ui less than, each magnitude ui is less than or equal to 1. Now, look at this, maximum value of magnitude ui less than or equal to 1, this implies magnitude ui less than or equal to 1 for all I equals 1 to, since the maximum itself is less than or equal to 1, it means that the magnitude of each component of the vector u bar has to be less than or equal to 1 naturally. Okay, since the infinity norm, L infinity norm is less than or equal to 1. okay, and that gives us a very interesting expression. So, this is less than or equal to summation I equal to 1 to n magnitude Zi, and in fact, so that gives us the expression that Z bar transpose U bar is less than or equal to summation magnitude Zi. Now, does the maximum occurs? Yes, maximum occurs if you think about it when magnitude ui equal to 1 for each I, that is for all I magnitude ui equal to 1, and the sign of ui equals sign of Zi. That is what you are doing is, if Zi is positive, you are setting ui to be plus 1. If Zi is negative, you are setting ui to be minus 1. That is ui equal to plus 1 if Zi is greater than or equal to 0, minus 1 if Zi is less than, that is ui is basically equal to, you can say in some sense, sign of Zi, alright, okay. And in that case, what is this? You can see the maximum value is achieved, and what is the maximum value? Maximum value is nothing but the L1 norm, that is the L1 norm. And therefore, what you observe is something very interesting. What you observe is the dual norm of the infinity norm equals the L1 norm, okay. So, the dual norm of infinity norm of the L infinity norm is the L1 norm, alright. And similarly, you can work out the dual norm of other norms. So, for instance, what is the dual norm of the L1 norm, and you should be able to convince yourself that it is indeed the L infinity norm. These are the duals of each, alright. Let us look at another problem, problem number 8 or example number 8. We want to derive the dual optimal problem corresponding to general LP. So, we want to do dual of a general LP, or that is your general linear program. Dual of general linear program, and this can be found. Now, consider your general linear program, that is your minimum C bar transpose X bar, subject to the constraint that G X bar is less than or equal to H bar and A X bar equals B bar. Now, the dual problem, now what we want to do is, this is a general LP. General LP means it has, of course, these are component wise inequality constraints, okay. So, each element on the left, each element of the vector on the left is less than or equal to each element on the right, that is of H bar. So, this is so general LP means it has inequality constraints and it has inequality constraints and it has equality constraints, and therefore, if you look at this Lagrangian, you can formulate, remember, to find the dual problem. So, we want to find the dual problem for this. This is L bar of X bar lambda bar mu bar, and the dual problem of this is C bar transpose X bar plus lambda bar G X bar minus H bar plus nu bar lambda bar transpose plus nu bar transpose A X bar minus B bar. Of course, with each Lagrange multiplier lambda I associated with the inequality constraints greater than equal to 0. Okay. So, these are Lagrange multiplier these are the Lagrange multipliers for the inequality constraints. And we have seen something similar before. We have seen the linear program with only equality constraint but not inequality constraint. Of course, these are vectors because you have for each one Lagrange multiplier for each lambda bar, one Lagrange multiplier for each inequality constraint. That is, if G is m cross n, then you have m inequality constraints, alright. So, therefore, you have m Lagrange multipliers, alright, and nu bar is basically one Lagrange multiplier for each equality constraint. That is, if A is m tilde cross n tilde, then nu bar is obviously m tilde. So, okay. So, one Lagrange multiplier for each equality, one for each equality constraint. And now I can recast this, I can simply rewrite this, just write this as x bar transpose, take the transpose of the whole thing because it is scalar quantity. So, I can simply write take the transpose of this, correct, x bar transpose into C bar plus x bar transpose into, well, I can write this as x bar transpose C bar plus, well, x bar transpose G transpose minus H bar transpose into lambda bar plus x bar transpose A transpose minus B bar transpose into nu bar, and collecting all the terms in x bar transpose, this is C bar plus G transpose lambda bar minus H bar transpose lambda bar, I am sorry, G transpose lambda bar plus A transpose nu bar minus, this will be the constant terms, H bar transpose lambda bar plus B bar transpose nu bar. Okay. And now you will observe something interesting. What you will observe is this is a linear function of x, okay, or in fact this is affine in x bar, okay, which means now we have our Lagrangian, remember, correct. If you look at the duality theory, now we have to find G of lambda bar mu bar, which is the minimum of the Lagrangian for each value of lambda bar comma mu r, that is for each Lagrange, that is for at every point corresponding to every lambda bar corresponding to a particular lambda bar mu r, that is Lagrange multiplier vectors. We have to find the minimum with respect to x bar. Now you can see this is affine in x bar, which implies the minimum equals minus infinity if the linear term, that is the coefficient, that is the vector multiplying x bar is not equal to 0, then I can take it to minus infinity by choosing appropriate values of x, because it is a hyperplane in x, correct. This is the equation of a hyperplane, alright, and by choosing, if this coefficient vector multiplying x bar is not 0, then by choosing x's appropriately I can always take it to any straight line or hyperplane, I can always take it to minus infinity. Okay. So, this is minus infinity if C bar plus G transpose lambda bar plus A transpose nu bar is not equal to 0. On the other hand, something interesting, now minus infinity is also a lower bound. Remember, g of this thing lambda bar nu bar is always a lower bound. So, minus infinity also lower bound for the original problem, but it is not very interesting because minus infinity is a lower bound for any optimization problem, but it is not very, let us put it, useful. It is not very useful. So, instead we want a certain lower bound which is more useful, and that you will get by considering the other case when C bar plus G transpose lambda bar plus A transpose. So, a more useful lower bound, more useful, let us say lower bound is, well, if C bar plus, when C bar plus G transpose lambda bar plus A transpose nu bar equals 0, then the lower bound is, this is a constant, therefore G lambda bar mu bar in this context, in this case G lambda bar mu bar equals, well, what is it? It reduces to the constant, which is minus H bar transpose lambda bar plus B bar transpose nu bar. Okay. And therefore, now, so this is a lower bound, this is a lower bound. What does this mean? This means that for any lambda bar nu bar, and of course lambda bar has to be, remember that constraint is always there, lambda bar has to be component is greater than or equal to 0. All the Lagrange multipliers associated with the inequality constraint have to be greater than or equal to 0. So, for any such lambda bar mu bar satisfying this constraints, alright, G of lambda bar mu bar is a lower bound for the original optimization. And therefore, what is the best lower bound? That is the dual problem. So, the best lower bound, which means something that is close. So, everything is a lower bound. What is the best lower bound? Something that is the maximum value. So, everything, so you can, if you remember the picture, this is the original problem which is convex. This is the dual function, and this is always a lower bound, okay, for any, the entirely lies below the optimal value. So, this is the primal optimal. And this right here is D star, which is the dual optimal, and this is what we call as the best lower bound, because it is closest, it is the one that is closest to the optimal value P star of the primal optimization problem. And of course, if D star equal to P star, that implies that the duality gap is 0. The primal optimal equals the dual optimal. Okay. P star equals D star implies duality gap equal to 0. And therefore, the dual problem is basically the best lower bound, which is maximizing G bar lambda bar mu bar, which in this case is, well, C bar plus G transpose lambda bar, I am sorry, which is in this case is, and observe that the dual function, this is concave, okay. So, G lambda bar mu bar, so this is minus H bar transpose lambda bar minus B bar transpose nu bar minus H bar transpose lambda bar, I am sorry, or you can write plus, but this is brackets, minus H bar transpose lambda bar plus B bar transpose nu bar, negative of the whole thing, okay, that is the constant. So, minus H bar transpose lambda bar, I am just going to write that like this, minus H bar transpose lambda bar minus of H bar transpose lambda bar plus B bar transpose u bar. But of course, you have constraints, subject to the constraints that, remember, this is only when C bar plus G transpose lambda bar plus A transpose nu bar equal to 0, and of course, each lambda bar is component, each lambda is greater than or equal to 0, or lambda bar is component wise greater than or equal to 0, and this is the dual problem. And you can see this is concave, because it is a linear function, linear in lambda bar nu bar, so it is both convex and concave. Alright, in particular the dual problem is concave, and therefore you can find D star, this gives solution equal to the optimum value equal to D star, which is in fact less than or equal to P star, but in this case D star will be exactly equal to P star because it is a linear program, which is a convex optimization problem. So, in general, for a convex optimization problem, strong duality holds, which implies that D star equal to P star. Okay, all right. So, we will stop here and continue with other examples in the subsequent modules. Thank you very much.